Hi, let's now start Module 10, Renewable Energy Forecasting Advanced Topics, with its first block, from linear to nonlinear regression. We have learned previously about the linear regression case to model a relationship between explanatory variable and a response variable so as to be used for forecasting. Let's look at this motivating example. We have obtained input-output pairs, so values for an explanatory variable x and a response variable y over the last 200 time step. Let's assume we want to use this data that we have collected, we have 200 points here, to model the relationship between x and y so that when we get new values of x, we're going to use them to predict y. Based on this scatter plot, since we know about linear regression, we're now going to try to fit a line through this cloud of points. And if we use linear regression with least square estimation, we should find the best line that describes this cloud of points. This is what is done here, and we obtain this red line. That's the best line that describes this cloud of points. It doesn't look that good, but we have made actually a quite stiff assumption on the relationship between x and y. What is going to happen if we were to use this relationship as an input for forecasting future values of y based on new values of x? Since the model fitting is not very good, this line doesn't describe very well the cloud of points, what is going to happen is that our forecast will most likely not be very good. So this is not such a good idea to use linear regression if there's some basis to think that the relationship is not linear. Now let's start from the basics, the linear regression, which we already introduced, and we'll see how we can generalize that to nonlinear regression case, especially polynomial regression. A simple linear relation can be assumed between a variable x and y, and this is used as a linear regression model. The relationship is written here as yt equal beta 0, the intercept term, plus beta 1, the slope, times xt, and this for each time t that we have observed in the past. On top of this relationship, we have a residual, which is the noise on top of the relationship itself, and this noise is centered on 0 and with finite variance. A linear regression model can be reformulated in a more compact form, and it's easier to handle. There yt is equal to bold beta transpose times bold xt plus the residual, and this for each time t in the past for which we collected data. There, bold beta is a vector that is composed by the two coefficients, beta 0 and beta 1, and xt is a vector that is composed by 1, so it's going to be 1 times the intercept, and xt, so the measured value of x at time t, because it's going to be multiplied by beta 1 through this relationship. When we've established this linear model, we can use least square estimation to find the best value of beta that describe the cloud of points. There are a number of assumptions that we overlook here. You can read in test books what are the assumptions for least square regression, least square estimation applied to linear regression. But eventually, what we're going to obtain here is a least square estimate beta hat for the linear regression model. It's going to be the estimate that minimizes a quadratic loss, so a sum of squared errors. These residuals can be rewritten as the difference between the measurement, yt, and bold beta transpose times bold xt squared, obviously. And there is a closed form solution, analytical solution, to find this parameter estimate, which is given by this expression. In this expression, bold x is the so-called design matrix, which has all the values for the input vector bold xt for the various times in the past transpose. So here, this would be the vector xt for the oldest time in the past, and here you have the vector xt for the closest time in the past. There, this is the response vector that concatenates all the past values for the response variable with the time instant corresponding here. So for the first line, the oldest time, the second line, the second oldest time, etc., to the time that's the closest to us. Eventually, beta hat is composed by beta hat 0 and beta hat 1, which are the two parameter estimates for linear regression model. Now that we have our basis right, we could actually assume more generally that instead of using only x as an input variable, we can design features that are x to the power of 2, x to the power of 3, etc. So this is the idea of polynomial regression, that we are going to look at extending the possibility to use x with different power values. We can write a polynomial regression models consequently in this way. So we try to explain yt as a sum of an intercept as before, and then a sum of coefficient times xt at the power p. So if p equal 1, that's beta 1 times xt as before. If p equal 2, that's beta 2 times xt square, etc., etc. Besides this polynomial regression relationship, we still have a residual component. As for the other case, the residual is assumed to be centered and with finite variance. We can also reformulate this model in a more compact form, and this is going to look as for the linear regression case we had before. Yt is equal to bold beta transpose times bold xt plus the residual component, where this time bold beta is the vector for all the coefficients. We have p plus 1 coefficients or model parameters, and xt is a vector for all the values of the explanatory variable at the power 1, 2, etc. Least square estimation can also be used since the model is still linear, and under the same assumption we will obtain the least square estimator for our model parameters. The expression here is similar to before, except that the model here is different from our basic linear regression model. There are more components here that enter this multiplication, but the solution, the closed form solution for parameter estimate, look the same. We only have to assemble the matrices in a different way. The vector of parameter values we want to estimate is of dimension p plus 1. The design matrix here is quite wider than before, since for each and every time instant, instead of only 1 and the value of x, we also have to take the value of x squared, x power of 3, etc., etc., to the x power of p, and this for all the time instants. For the response variable vector is still the same as before. Let's now apply this idea to our example. We are going to choose to apply polynomial regression with p equal 2. So that's quadratic regression, and then p equals 3. That's cubic regression. On the left side, the red line is the solution we obtain after estimating the model parameters with quadratic regression. On the right side, this is the solution we obtain when estimating the parameters for cubic regression. In both cases, they look quite nicer than the linear fit. I think we can agree on that. Actually, here we're quite lucky. The relationship truly was quadratic. So when fitting higher order polynomials, like for the case of the cubic regression, the values of the parameters that we estimate are actually 0. But in general, one should be careful, since if trying to fit high-order polynomials, one may obtain spurious results, like waves at the beginning and at the end of the cloud of points, or maybe even waves in the middle of the cloud of points, since the polynomial regression we try to overfit the cloud of points. Let's look at a more general nonlinear regression case. This is a power curve, not a real one. This is an artificial power curve, but it looks like a real one. X here could be wind speed forecast, and Y here could be power generation. Now let's apply polynomial regression, and since we've heard that power curve should be cubic in the wind speed, then we're going to consider that we should use polynomial regression with p equal to 3, so cubic regression. Here, this is the result we obtain after parameter estimation, and that shows what type of spurious results I mentioned before. Instead of nicely following the power curve all the way, it seems that at the beginning of the power curve, the curve is going below 0, so it's a start before the steep slope part. Here, it doesn't manage to follow properly the steepness of the power curve, and eventually we obtain this bump at the end where the cubic regression overshoots and then is just bending backwards, so not really following the shape of the power curve. So could we not find some other way to fit polynomial regression or some other type of nonlinear regression that permits to model this kind of power curve but without this kind of spurious effects? Do you have some idea? What we can do is that we can do local polynomial regression. So instead of fitting a polynomial regression for the whole power curve or the whole data set, we're going to localize the fitting of our model. For that, we're going to consider a number of fitting points. So let's say here our fitting points could be at 0, at 0.1, at 0.2, at 0.3, etc. until 1. So we have 11 of these fitting points. Eventually, we'll use some weighting function that will permit to give more or less importance to the various data points to make sure that when we fit a model, it's locally around a certain fitting point. And eventually, when we fitted all these models, we're going to connect the different models so as to reconstruct the full nonlinear regression curve. Let's do it step by step. We're going to concentrate first on the fitting point at location 0.6 here. We have a weight function which is drawn here in blue, and this weight function will give more or less weight to data points that are away from this fitting point. That defines a neighborhood around this fitting point. When points are close to the fitting point, so let's say just here, this is the weight that we should give to the fitting point in the learning, so in estimating the parameters. So here for a fitting point that is just a little bit away from the fitting point, the weight will be very high, maybe 0.9, around 0.9 here. But for learning the relationship around this fitting point, if we use data points that are here, so let's say after 0.4, a bit below 0.4, the weight value is going to be 0. So that means this data point is not going to be considered in the learning for estimating the parameters. In this example, we use a weight function which is a Gaussian kernel. The expression of a Gaussian kernel is given here, and when you use such a Gaussian kernel, there are other type of functions that are possible for weighting, but when we consider this type of Gaussian kernel, these are defined by a location, that's the fitting point, and some scaling, and that would be the standard deviation or the variance. Here the standard deviation is equal to 0.05. When we have localized our fitting point, we have associated a kernel and defined some weights to the different data points, we can generalize the use of least square estimation and then use weighted least square estimation. The point of weighted least square estimation is to account for these weights we've been giving to these data points. For the polynomial regression we had before, the weighted least square estimate is going to be written as beta hat, like before. It will minimize the sum of squared errors, but these errors will be weighted. Each and every error is weighted by the value of the kernel function at the location of the data point. If you develop that, we have the weight appearing here, and this is the residual from before, so measurement minus the model output. And still, we have a closed form solution here, similarly to least square estimate, except that we have a weight matrix that appear here that we didn't have before. So the matrices are formed in the same way as before, matrices and vectors. We have beta hat, which is our vector of model parameters, their estimate. The design matrix, which gives the value of the explanatory variable for each and every time in the past, so in the data set. The response variable vector with all the values for the response variable in the past. And eventually this weight matrix, which is a diagonal matrix for which each and every entry on the diagonal is the weight to be given to this data point for each and every time in the past based on this weighting function which we use to be a kernel. Let's apply it to our case and to a few fitting points. So first, let's look again at this fitting point at xu equal 0.6. And let's say we're going to consider a polynomial of degree 1. So it's like fitting a line. It's like using linear regression. But now it's the neighbor in the neighborhood of this fitting point at 0.6. When fitting the model in this neighborhood, remember that we are done weighting the data as we go away from this fitting point. It seems that we managed to locally represent the relationship between the explanatory variable and the response variable, and we obtain this line. We can keep the value of the model at the location of the fitting point for making these connections afterward between all the models we're going to fit. Now let's assume you could also fit a polynomial of degree 2, for instance, at another fitting point. So that would be in this case here. We define a fitting point at 0.2 and want to fit a quadratic model locally. We have a weighting function that is going to give more importance to the data around this fitting point and less important to the data that is further away in this direction and in this direction. This is the model that we obtain, and we can keep the value of the model at the fitting point. If we were to repeat that, given a choice for a polynomial order, a choice for a kernel and its parameters, and also a choice for a number of fitting points and their location, we could actually fit our model at these different fitting points. So here we have quite a lot of fitting points, as you can see, and every time these squares are for the results of the model output at the fitting point location. And we're going to connect these various points at which we've been fitting local models. And you see, as we connect them, we obtain this very nice nonlinear regression curve that can describe precisely what this power curve is without the spurious effect we had in the case of aiming to fit a single polynomial regression to the whole curve. Thank you very much. Now I would like to invite you to use the self-assessment quiz to check your understanding.